And welcome. Really thank you for joining our talk. It's late, but I hope you will find it interesting. Today we will talk about some use case that Florin and I conducted using multiple JVMs, in particular different compilers. And we will tell you what are, in some specific areas, the strengths or the weaknesses of those. The agenda is packed like that. We have chosen a set of those benchmarks. In a nutshell, this use case, what it is about, I will show you here. So we have everything publicly available. We wrote a bunch of benchmarks, everything is here. And with these benchmarks, we try to assess the compilers. And we have three flavors of those compilers. And we will try to bring on the table for today what we think it's most useful to you as an application developer. And at the end, we will also end up with some conclusions, challenges, and what we learned so far, because it was quite interesting to us. Few words about myself. My name is Ionuț Baloșin. I work as a software architect for Raiffeisen Bank International. And besides this, I'm involved into these technical trainer activities. Overall, I have 4 topics in my catalog. And yeah, if you are interested in one of these topics, you can get in touch with me.
And I'm Florin Blanaru. I'm a senior software engineer at Scalar AI. I'm a previous Tornado VMX contributor, and in my spare time I look into language runtimes, compilers, and I do performance analysis and tuning.
Good. What we will talk about, as already have said, it's public anyway. So we have here on my website, we have the article, the full article, because there are a lot of use cases and the in-depth analysis is here, so you can see there is quite a lot. For today, we will try to resume to what we think it's a bit of useful to you. 2 points to make here. We try to trigger this analysis only on LTS version so far. So therefore, today's content, it's bound to JDK 17. Are you using a newer JDK version after 17? Do you use 17? Okay, free. Oh, okay, good. Then this is for you. Then this talk is for you. One more aspect. Maybe you have already asked why not 2021. The reason for that, we didn't have time to prepare something for 21. To have something, such article ready, for us means really a lot of work. We already started with the benchmarks. We have started running them for 21, but they still didn't finish. It takes a few weeks to run for all these JVMs that we target, plus the analysis takes probably more than 1 month. So in a nutshell, we hope to release something beginning of December. That's why we don't have anything yet for 21, because it's really a lot of work. But anyway, this is, as you already said, you are using 17, so I think it's perfect match. What are these compilers? Yeah, the first one is it's C2 from OpenJDK. The second one in the middle is called Graal, and it's embedded in Graal VME. This is the former name. Recently, they rebranded, and it's called Oracle Graal VM. Nevertheless, within this talk, I will still use the oldest terminology, because this is this is how it was when you run these benchmarks. So when we run these benchmarks, we used 22.3.0, and back then it was called Graal VME, but it's just terminology. And the last one is the Graal VM compiler from the community edition. Which one of these JVMs do you use? Do you use OpenJDK? Yes? Yes, good. Who is using Graal? Okay, but there are some people missing. What are you using? OpenJ9 for? Or you don't know? Or Azul, Zulu, or Prime? Zulu, okay, good. Yeah, so, but in a nutshell, what you have in Zulu, it's hotspot based, it's C2 actually. So you end up in this, the first use case in this path, yeah? All the others, depends if you use the community edition or the enterprise edition, here it's clear. When we started with this use case, to make it a bit more comprehensive but also relevant to the people, we did choose two types of architectures. The first one, which is based on x86, which is probably the most common one, right? Most of us are running using on this one, but we also run this on ARM64. And this is, for example, a newer architecture. It comes, for example, with M1 chipset from Apple, but also in cloud. I noticed this tendency of moving towards ARM because it's a bit cheaper. Nevertheless, the topic for today is focused on x86 as the most common platform today still. All of these benchmarks were run using GMH. Have you heard about GMH, Java Micro Benchmark Harness? Okay, few, good. This is actually a library that you can use. It's more or less annotation based that you can use to do micro benchmark. So for example, you have a tiny little method, and with this tool you can for example, detect how much time it takes in the optimal condition that method to run. So we use that one with the version that it's specified there, and as said already, everything is public on this GitHub. So you have here all the benchmarks. Yeah, that one is the logo, and everything, all the tunings, because when we run it, for example, on Linux, on x86, we tune also the operating system. For example, we disable hyper-threading and turbo boost to have consistent results, and so on. So everything is explained here. If you want to run it on your own, on your personal PC, it should work. And let's talk about a few benchmarks. Therefore, we have chosen 7. Yeah, the first one, the first one is called infrastructure baseline benchmark. This is very, very important. Every time when you do, especially comparisons across JVMs, like we did, I mean, across different compilers, it's very important to understand if the infrastructure, I mean the baseline, is the same. What it is for us, this baseline, maybe I have to zoom it a bit into the code. So this is one test. As mentioned, this GMH is really annotation driven. And what we try to measure here is just, for example, how much time it takes to call an empty method. How much time it takes to call a method which calls another method which is being either in line or not in line. And so on and so forth. So we try to add to this baseline all the possible use cases that we are using across all the other benchmarks, because then we want to see if everything is the same. And as you see here, just to explain a bit, this is a bar chart. And this is actually, you have it grouped by 3 bars. Each color represents, for example, a machine. The yellow one, this one, it's for Graal Community Edition. This orange one is from Graal Enterprise Edition, and the blue one it's from Hotspot, for C2. Another aspect, because we are measuring here the average response times, shorter the bar is, of course, better it is. Because if it is longer, it means more time it took, so it's not good. And as you can see here, for all the cases, it was exactly the same, almost the same, except this object sync method with very, very tiny differences. I'm not sure if this is the right font size, but it's just a sub-nanosecond difference, so I would say it's not relevant at all. So this was for us the baseline. It's important to have the same baseline when you compare across different compilers. And the first interesting benchmark was this Enum value lookup benchmark. I'll try to explain it a bit. And let's see what we have here. This was inspired from real use cases. We are using, for example, enums, right? We always declare enums. And at some point, we want to convert, for example, some string fields to an enum entry. And this happens especially if you create RESTful APIs and you get a request. That request is deserialized, and if you have a field which is mapped to an enum, this is what happens actually. The field itself, it's trying to be matched to the corresponding enum entry. And therefore, you can do this in two flavors. Yeah? You can do using enum.values, which is the JDK API. So this one gives you an array with all the enum entries, and then you can iterate through them and compare using the equals. If that one is equal to the value you got, you just return the enum entry. The thing is, you're familiar with this code, right? This is common. The problem with this approach is it's not very efficient performance-wise, because every time when you call dot values on an enum, it creates always a new array. So it creates a lot of allocations. To circumvent or to optimize this approach a bit, you can use a cached values, and this cached values is this one. You can see I'm declaring a static final array of cached values, and then I just iterate through it without, actually this avoids allocations. This is the difference between these two flavors. So we did this, we ran our benchmark. Should I zoom it a bit? This is better, I guess, yeah. And what results we got? The results were like this. So in the implicit form, in the just default, calling enum.values, I would say it's not fundamentally different between Graal E and C2 from OpenJDK. Nevertheless, here the Graal C was lower. But what is interesting is, okay, even in the optimized version, when we used cached enum values, we have quite a big difference between Hotspot in SNC2, which was better than Graal and both Graal compilers. And the question is why? This is interesting, and what we had to do, fortunately or unfortunately, yeah, sometimes it's fun, sometimes it's really a lot of work. We had to actually print both the compilation, so we had to have access to the compilation log, but also we need to go to the assembly and study the assembly and see what happens. Because otherwise it's very hard to grasp. And in such particular case, why JIT was faster was basically because under the hood, to compare those strings that I've showed you, to do this string comparison, equals comparison, they are using different intrinsics because there are different compilers, different intrinsics. So the one used actually by C2 was better in regards to the one from Graal, which was actually relying on some, to compare these values, Graal used like a bitwise approach on some regions. So basically they took both regions and compared bitwise to decide if those strings were equal. And this is a bit slower than the version from the C2. In a nutshell, if you have such a code, of course, you cannot influence, you can just choose the compiler by yourself, but I would say if you have this case, try to cache these values, especially if you use this in loops. Yeah, or very frequently, because you create a lot of allocations. So try to use cached enum values and not calling the API always. This was the first one. Second one was log coarsening. Log coarsening, what it means. This is about, better to show you the code, yes. Let's suppose you have a method, yes, which looks like this. Synchronize, 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 synchronize. Have you ever wrote such code? No. Can you have this happening at runtime? Yes, you can. And explain. Imagine you have a tiny methods all containing synchronize this, and you call from one, you call the other one. The thing is, even if at the code level you don't have such pattern, due to the inlining, after inlining it's triggered, you will end up with such a code. Therefore, we just wrote the method in the shape how it would appear after inlining kicks in. Therefore, as you can see here, this synchronization, it's really useless. It doesn't make any sense, right? Because you have it once and it's the same log, so it doesn't help if I have a subsequent ones. How this code looks like, this was a bit of interesting. I will show you just one use case without really complicating the things. Have you heard about biased locking? Biased locking was an optimization in former times, starting with 1.5, 1.6. Programmers didn't know how to properly actually do this synchronization. It was really hard in the past to work with concurrency. And they put synchronized everywhere just to be on the safe side. The problem is back then, because the hardware was not so good, synchronization was costly. So even if you abused of using synchronized, this has a performance penalty. And this optimization actually help that if there is no contention, if there are no threads using the same synchronized block, it's actually for free. So you can put synchronized all over the places if it is the same thread, that is for free. And it's an efficient scheme of handling. The problem is nowadays it collapses or clashes with other features. And therefore they decided to remove it. On top of this, the reason is on modern hardware, this should not be anymore a pain. Yeah? And this is removed, and I will show you the default use case without bias locking, I mean without this optimization. It was deprecated in 15, and now in 21 it's completely removed. Yeah? In 17, you still have the flag, you can disable it explicitly. Enable it explicitly, sorry, because it's disabled in 17, but in 21 it's disabled. And the thing is, I will focus only on this nested synchronize, only on this method. Yeah. The thing is, why, for example, one compiler it's way slower. It's 2 orders of magnitude slower than the others. For example, Graal E, it's very fast. This one is the fastest one. But the C2, it's 2 orders of magnitude. This is a tremendous difference in time. And again, the answer it's not so trivial. We had again to take the compilation log, and in the compilation log, if you enable that one, it says explicitly. The compiler tried the compiler, the C2, hit an optimization budget. Therefore, that method was left, and the running of that method continued only in the interpreter, in the template interpreter. Therefore, this is so slow in comparison with the other version that gets optimized. So this is basically the difference between a method running in interpreter, this method running in interpreter, versus the method being compiled. This is why it's so slow. And there is one more interesting case, as you see here. Yeah? Let's go back. You see here, you have a lot of additions here, and these synchronized blocks. And why, for example, Graal-E, it's so fast, it's because it really does a nice optimization. So this is the snapshot of the assembly. What it does, it actually it checks only once if that lock is biased to another thread. And that one is just with a compare and swap operation. That's it. It's a CAS. It's an atomic operation. Everything else, this add are the additions that corresponds to this result plus increment value. So therefore, even if you put synchronized, it's optimized in the way that everything it's coursed, yeah, because it's called raw coarsening, and you don't pay the cost of this useless synchronization. But again, it really much depends on the compiler, because if you end up with such a use case in C2, for example, it's very slow. The next one, which is called dead local store. What it does, let's suppose you always, when you write methods, you allocate objects. And it might happen in some cases that you allocate something, you set the reference to one, you set the reference to that object in one field, and in the subsequent instructions you set again. So basically you reset the value. And I will show you how it works. So let's suppose you have these objects allocated, yeah, from 1 to 8. These are allocated in line, yeah, 8 allocations. And then in this, you pass the references, the values to a wrapper, to the constructor, and the constructor is this one. In the constructor, sorry, this one, it is the constructor. In the constructor, what you do? Of course, this is intentionally written like that. You call the default constructor, which default constructor again allocates and then sets the references to the initial objects received as parameters. Therefore, all the allocations in this default constructor are useless. Correct? Because you receive some objects as parameter, you call a constructor, you allocate, but then you reset the references back to the values received as parameters. And this is the thing. If the compiler should detect this use case, so the compiler should see, okay, if it is able to inline this, it should eliminate all of these allocations. But what happened in our use case, let's go back and see it here. In our use case, okay, so in the case of just returning the object itself, which is this one, sorry, I'm jumping, wrapper object baseline, which is, where it is, object wrapper baseline. Yes, so this one just returns a new wrapper, and this new wrapper, what it does, it allocates all of these objects. In such a case, actually, GraalE, it's way faster. I mean, not way faster, but it's faster than C2 and Graal from Community Edition. And the reason is because Graal from the Community Edition, it's able, yeah, this is a bit of assembly, but in a nutshell, it is able to group the instructions to be very CPU friendly. In what it did, it grouped the loads, it grouped the stores, and this is why if you have this grouped, you actually take advantage of the CPU prefetching and pipelining, for example, and it runs much faster than if your instructions are interchanged, load with stores, stores with loads. And this was the reason why it's so fast. And in the second case, when it is this wrapper object that store allocation interprocedural, again, Graal was faster. And the reason for that was, again, it does nice optimizations. It groups a bit the way how it allocates the objects. In a nutshell, all of these objects, when you have an object to be allocated, the TLAB is inspected. The TLAB is like a thread local allocation buffer, so each thread allocates in the thread local allocation buffer. And what Graal does, because there are 8 objects to be allocated, Graal does some optimizations that checks only in the beginning, for example, if all of those fits inside that buffers and inside that buffer, and then allocates them subsequently. And this is what it's called fast path allocation. If some of the objects do not fit in the TLAB, it's an explicit check, yeah, TLAB size in comparison or compared against current TLAB plus the size of the object. And therefore, this is called slow path allocation, and that's why with this kind of trick, it ends up in having a shorter response time than the other. So in a nutshell, this use case was in favor of Graal from the Enterprise Edition. It behaved better. Yes, now I will pass it over to Florin because he has some other interesting benchmarks to show you.
Right, thank you, Ionuț. I'm gonna show you 3 more benchmarks and then we jump to conclusions. So hang on with me. The next one is called the MP throw benchmark. This one tests if pretty much throwing a null pointer exception in a hot loop in a method and then catching it in the caller. It tests the performance of this kind of stuff. So let's see the code. Sorry, I'm one-handed here, so it's going to be a bit difficult for me, and this is not my laptop, so. Right, so as I said, we have 2 benchmarks, implicit throw NPE and then explicit throw NPE. As you can see, we have a hot loop here. We iterate over an array of objects called A, and then we do a try-catch in both of them, and we call either implicit throw NPE or explicit throw NPE with each object in the array. In the explicit one, we check for null, and then we throw a null pointer exception if the object is null. Otherwise, in the implicit one, we just access a field directly. O can be null, so we might throw a null pointer exception here as well. So let me jump to the article and see what numbers we get. We also have a threshold in our tests. So for threshold 0, then the whole array will never contain any null objects, any null values. For threshold 0.5 is going to be 50%. For threshold 1, all objects are going to be null inside, all references are going to be null inside that array. So let me see, how can I increase the font? Yeah, sorry. The keyboard is in German, so...
Sorry for that.
Yeah, no worries. I hope you can see, yeah, you can. No.
You can just click on it and it's opened in a different one.
All right, awesome. Thanks. Well, we can see that for explicit throws, all 3 compilers are pretty much very close. in terms of performance. However, for implicit throws, when we have nulls inside the array, we can see that C2 is much faster than Graal, both Community Edition and Enterprise Edition. So we need to look into why this is happening. We use a tool called Async Profiler for that, and we generate some nice flame graphs, I would say, which shows us where we spend most of our execution time in those benchmarks. So I'm gonna open the first flame graph, which is for Open JDK, right? As you can see here, we have the stack trace, we have the benchmark called NPE throw benchmark implicit throws, and then we kind of have this up to runtime handle exception C, which is the exception handler in the JVM. So we jump directly there with C2, which is the fastest one. With with Graal VM, both Community Edition and Enterprise Edition, we, however, as you can see here, we have a different flame graph which shows where we spend most of our time. This is going on in the null pointer exception fill in stack trace. We fill the stack trace and then we call into JVM CI, which is this Java interface for the compiler because Graal is written in Java. So pretty much what's going on here is that Graal will always fill in a stack trace if you implicitly throw a null pointer exception, while C2 has this optimization where it's sometimes for implicit exceptions it's not going to fill in the stack trace. That's why it's much faster. By the way, you can disable this in C2 with this omit stack trace in fast throw flag, and then you're going to see the same performance. Next benchmark is recursive method call benchmark. This one tests the performance of recursive method calls in classes, interfaces, and lambdas. So again, let's look at the source code, and then we jump to the article. Right, so we have a couple of benchmarks in this class. We have static and non-static calls, recursive calls for lambdas, in I calls and V calls. This is how a benchmark method looks like. You go up to a certain def and then you just return a static field object. Now, for lambdas, all three VMs are able to pretty much directly return the result. They inline and they optimize the result, so they just return a constant usually. But we can see some very big differences between C2, Graal, and Graal VM EE and Community Edition. And those differences come mostly from the fact that C2 will always do a virtual call, so it does no tail call optimization, while Graal will kind of inline and is gonna jump, is gonna do a recursive call of a different def than one. So for example, this is the assembly code for Graal VM CE, which is gonna do jumps 6 by 6. So pretty much you call 6 methods in on each recursive call in the assembly code. Sorry. Right. And finally, the last benchmark which I'm going to present to you is the Scalar replacement benchmark. This one, it has the ability of the compiler to perform escape analysis and scalar replacement. I'll have to define what escape analysis is and what scalar replacement is. Escape analysis is pretty much an analysis phase which is done by the compiler, which looks at a method, let's say, looks at the allocations inside the method and checks if any allocation escape as an argument or escape from the body of method. The scalar replacement is enabled for objects which do not escape. So that means that you can stack allocate the object and you don't have to do heap allocation, so that saves you from heap pollution sometimes, right? So in this benchmark, we have two wrappers. We have a light wrapper and a heavy wrapper. The light wrapper contains two fields, F1 and F2. Then we have the heavy wrapper, which also contains a byte array. And then the benchmark cases are no escape, where you just allocate a light wrapper, and then you return the sum of its fields. In this case, for example, W never escapes the body of this method, so escape analysis is going to signal this, and then a light wrapper is going to get stack allocated, right? No escape array object is the same, but we also access the array length in the heavy wrapper. Then you have branch escape object, where we have an allocation of a heavy wrapper, and then we have an if-else condition. Object escapes is always false, so this branch is never taken, the true part is never taken. We always return a cached wrapper. So this pretty much boils down to the compiler being able to move the wrapper allocation inside the true branch of the if condition. If the compiler manages to do that, then wrapper will not have to be allocated. Otherwise, it will be allocated. And then we also have an arg escape object. This one boils down to whether or not you are able to inline this equals method of wrapper. If you are able to do that, then you'll have no object escaping the method, because you return this match. Otherwise, wrapper 2 is going to escape to the equals method. So now let's look at the results that we've got. So as you can see, in the case where we do no escape, or we have the no escape array object, all three VMs perform pretty much the same. However, in the branch escape object, C2 performs way poorer than Graal. And this is because, as I was showing earlier, in the branch escape object, Graal is able to move this allocation inside the false branch, so it never performs it, while C2 always does the allocation. Because it just leaves it here, it doesn't move it. In the scenario of the arg escape object, then Graal is able to just return true always, because it inlines, while C2 always allocates again. Right. Next, I'll leave it to Ionuț to tell you the conclusions of this.
Thanks, Florin. Yes. Sorry, my voice is still bad. As you saw already, or have seen already, we did a lot of these benchmarks. Yeah. The problem was how we can quantify at the end who is better than the other, because you are tempted to say, okay, I'm curious to see in general who is better, yeah? And this is not very easy, because there are some use cases when, for example, one compiler is better than the other, and some other test cases when the other compiler is better than the other. And then we try to search a bit how we can quantify all of these benchmark results in a more accurate way to, let's say, end up with some sort of classifications. Therefore, we found this paper, How to Not Lie yeah, with Statistics. This is an old paper if you Google for it, but the thing is, this is a mathematical paper. It's based on statistics. And this is not old-fashioned, yeah. Therefore, we got this idea from the paper itself, and we don't use the mean, because we could have used, for example, the mean to sum up all the benchmark results and to divide by their number. The problem with this approach is if you have a lot of results which are very much divergent, so the range is very broad, 1 second, 100 of second, 10 seconds, 200 of seconds. The mean is not an accurate way to quantify. The geometric mean, it's a better one because it shows you the tendency. Yeah, it shows you where the majority of the results are. So it's able to actually remove the outliers out of this result set. And this is the formula. We apply this formula across all of our benchmarks results on each architecture on x86, and we were able to come up with some sort of classification, but take it precautiously. Take it with just not take it for granted. Say, I have this one, definitely it's better, for example, one and not the other. This is what we got. In a nutshell, compiler from GraalVM E, the newer name is Oracle GraalVM. They rebranded it. This one was the better one, C2 was somewhere in the middle, and the community edition was the slowest one. And here on ARM64, it's more or less the same tendency because it's very hard to compare between x86 and ARM. These are different architectures. What we were interested in just to find the trends, to see if the same classification it's kept. And it was actually, GraalVM was still on top. And then we thought, okay, but let's come up with some more real guidelines for the people, for the application developer, because of course we have a lot of benchmarks, but it's very hard to grasp based on the benchmarks. It's hard to make conclusions for a software developer. Yeah? Maybe it's easy for a compiler engineer, but it's difficult for the majority of the public. Therefore, we came up with this kind of different categorization. In our opinion, when it's more suitable one compiler and in which cases it's suitable the other. For example, if you allocate a lot of objects, if you have a high degree of polymorphic calls. Polymorphic calls means calls with a lot of runtime target invocations. You have an interface with multiple implementations, so this is the case. Or if you have a lot of tiny, nasty recursive calls, for example, functional programming, all of this, Graal E, it's definitely better. Then C2, it's still good to handle exceptions. It handles those exceptions, especially if you don't use the stack trace of the exception. This is the case. It handles them in a better way than Graal. And in 17, because everything what I'm telling it's about 17, it's not valid in 21. It has an extended intrinsic set. So therefore, I would say in some use cases, C2, it's good. In others, the majority, Graal E, it's better. What we learned out of this, for us, I think the biggest benefit was the pleasure. I mean, we were really curious and we really learned a lot. But of course, it's very difficult to do all of this. It takes a lot of time, it takes a lot of analysis. And the problem is, if you try to reach some conclusions, you have to understand why. Just judging the figures, it's not enough. Also, what we learned out of this is, of course, there are differences between the architectures. So if you run on, for example, Mac, or if you use on Linux or on Windows, you might get different results. That's the case. One important point, we presented here only compilers. So we never talk about garbage collectors. We did that initially, so we had a set of benchmarks for garbage collectors. But the feedback that we received from the ZGC team, and they were of course fully right, was that using micro benchmarking to assess the performance of the collector, it's not good. Therefore, we dropped all the benchmarks for the garbage collectors. If I would have to do it, I will do it with real-world use cases, with a real load on those applications, but not micro benchmarking. That's why we just decided to remove the garbage collectors and focus only on the compiler optimizations. Of course, one of the other implicit benefits was we got in touch with a lot of people, yeah, and we are very grateful and thankful to, for example, JVM team, yeah, they really helped us a lot, and others that really spend time trying to understand. And provide us some hints. What we aim to do at the moment, as initially mentioned, we are in the process of running this on JDK 21. By then, we also extended the coverage of this benchmark. So at the moment, I think we actually increased with 40% of use cases, I mean on different APIs, because we try to be as more comprehensive as possible. And it is running at the moment. If you, for example, find this interesting, again, it doesn't matter to have any background in compilers. Just if you're interested and curious, you can contribute and help us. Because everything, it's public, it's open source, and we strive to have other people interested in contributing to this type of work. I think for us it was a real pressure. And everything have said, we thank you very much. If you want to get more into this, we have everything public, the article and the source code, it's on the GitHub. Thank you. And questions. I'm delighted to have questions. Nobody tries? Good. Then thank you. Have a lovely afternoon, and stay here for the closing keynote. I hope you had a great conference so far, and see you around. Thank you so much.